Hello, this is my reassessment video number 1 for Chapter 8 with Chapter 5, Oscillations. I chose problem 12 from Classical Mechanics by Taylor. It says, consider a simple harmonic oscillator with period tau. Let this denote the average value of any variable f of t, average over one complete cycle. Then they gave us the integral that we're supposed to use. It says, prove that the average of t equals the average of u equals 1/2 e, where e is the total energy of the oscillator. And it says, start by proving the more general and extremely useful results that sine squared omega t minus delta equals cosine squared omega t minus delta equals 1/2. Explain why these two results are almost obvious, then prove them by using trig identities to write sine squared theta and cosine squared theta in terms of cosine 2 theta. So these are non-driven oscillators, so we use this formula, and we plug in. They want us to first use sine squared omega t minus delta, plug that in as f of t, and then we have to use a trig identity to make it easier for us, so we can solve. We plug this trig identity in for sine squared omega t minus delta, and I went ahead and broke it into two integrals, because this integral ends up being 0, because once you take the integral of cosine, it turns out to be sine, and sine over a period is just 0. And then we just get this 1/2 t, and we have to make it go from tau to 0. So then we just get 1 over tau equals 1/2 tau, and then the tau's will cancel, and we just get 1/2, as we should have. So we do the same thing with cosine, except we use a different trig identity, but we still want to get it in terms of cosine, so we could still do that trig to make this equal 0. And then we'll get 1 over 2 tau equals t from tau to 0, and the same thing happens, and we get 1/2. So the only difference between the kinetic energy and the potential energy is these constants out front, and the constants aren't going to affect the integral, but I wrote it out just to be precise. So we do the same thing, and we plug in the sine squared omega t minus delta. I already pulled the integrals out in the front. We use the same trig identity, and then we end up using the same. Since we have it in terms of cosine, this will end up being 0, and we'll end up getting the same thing. These tau's will cancel, and then I left this 2 out in front, right back here. That way we can get in terms of the total energy, which is 1/2 ka squared. So that's why I left this 2 out in front and didn't multiply them. So that way I could get ka squared over 2 and just put that as e, and it's e over 2. I could have done it right here, but I didn't. I thought it would be better to show it at the end. Then I do the same thing for the potential energy, and I'll plug it in, the values in, I'll pull the constants out, and then I use the same cosine squared omega t minus delta trig identity, and this comes out to be 0, and then we get the same value. I left the 2 out in front, the 2 separated, that way I could put it in terms of the total energy. The tau's cancel, we get 1/2 ka squared over 2, and this is just the energy, so then we get the energy over 2. We get the potential energy is equal to the potential energy is equal to the kinetic energy, and if you add them together, it equals the total energy, and they're both e over 2.